going to go through examples 2 and 3 from section 6.1. Example 2 reads, graphing linear inequalities with vertical or horizontal boundaries. So here are two examples to go through. Graph the solution set for each linear inequality in a Cartesian plane. The first one gives you a whole bunch of information. But what's important out of this is the x minus 2 is greater than 0, and x is an element of the real number system, y is an element of the real number system. Now when it tells us that x and y are elements of the real number system, that's saying that there are no variables. They can be fractions, decimals, whatever, integers. There's no restrictions whatsoever in the variables. So that's going to dictate the shading and what kind of boundaries we're going to do. So first thing we can do here now is look at our inequality of x minus 2 is greater than 0. In the first example, recall that the first thing we did was create the boundary, and the way we did that was by dropping the inequality symbol and making an equation equal x minus 2 equals 0. So what we're going to do here is isolate x by adding 2 to both sides and put x is equal to 2. Hopefully you guys remember from back in grade 9 and partly in grade 10 as well. Then we have this equation x equals 2. That is going to be a vertical line that goes through that value of x is equal to 2. So now that we have our boundary done, we're going to be able to take that over to our graph. So we're going to rewrite the inequality as x is greater than 2. We're going to graph this. Now because equality is not possible, right here we just have x is greater than 2, not greater than or equal to, we can't draw a solid green line. We're going to draw a dashed green line, and that's again going to be a vertical line through x equals 2. Now as far as the shading is concerned, the shading for these vertical and horizontal ones isn't too difficult. Now we can do the whole substitute 0, 0 in to figure out which side where our solution set is found. But what we can do instead is just use some common sense. X is greater than 2. So where we're going to shade is all the values that are greater than 2. That's going to be to the right of this vertical line. So you can see, hopefully you have your book in front of you, you can see on page 298 of your book that our graph should look pretty much like that. Now they have it done a little bit nicer in the book in terms of the shading, but I still think I did a pretty good job. So that's A. Now we can take a look at B. Get rid of some of this stuff here. So the same idea for B. We can filter through the information that we need. This just tells us here that x and y are the two variables we're going to have. Right here is the inequality. Sorry, missed it. So here's the inequality right here. And it tells us that we have x and y are elements of the integer system. So let's come down here and we'll rewrite it. We've got negative 3y plus 6 is greater than or equal to negative 6. I think I missed it again. Negative 6 plus y. X is an element of the integer system. Y is an element of the integer system. So that's going to tell us there's restrictions on the variables. Again, our shading is going to be dictated by that. First thing we're going to do here is isolate y. So I'm going to subtract y from both sides here. That's going to leave me with negative 4y. Cancel this out over here. Negative 4y plus 6 is greater than or equal to negative 6. Let's go ahead and change that to an equal to sign so that we can find our boundary. So we have negative 4y plus 6 is equal to negative 6. We can subtract 6 from both sides to get negative 4y equals negative 12. We'll divide by negative 4. And we're going to get y is equal to positive 3. Now something that's important here. You guys worked with inequalities back in your younger grades. You probably did this before, but I'll just remind you. In an inequality, even though we were working with an equal sign here because we were trying to find the boundary point, ultimately though this was still an inequality. In an inequality, whenever we multiply, or in this case divide by a negative number, what happens is the inequality symbol becomes reversed. So now where we were originally dealing with a greater than or equal inequality, Because we divided by a negative number in this step right here, that's instead of greater than or equal to, we're going to reverse it. It's now going to be y is less than or equal to 3. Now we're going to go over and graph that. So the first thing we do is we find our spot 3 in the grid. Now we have to think about what kind of a line and what kind of shading we're going to do. Recall that from what we just talked about in that very last video, that whenever we have discrete variation, it's discrete variation because x is an element of the integer system and y is an element of the integer system. We're not going to draw a solid line. This time what we're going to do is a stippled green line. So our boundary is a stippled green line. So essentially we're just putting green dots on each integer intersection, if you will. So this dot right here is on the point 1 and 3. This one over here is at the point -2 and 3. Next thing we have to do is worry about our shading. So again, you could substitute the origin 0, 0 to determine, but there's no x value in an inequality. We just use our common sense again. Y is less than or equal to 3, so clearly we have to shade everything that is less than or equal to 3. Because equality is possible, we have this stippled green line, and we're going to shade orange. Now I don't have an orange marker, but I do have a red one. So I want you to imagine that this red shading that I'm doing here is orange. You guys are going to use your orange pencil crayons or whatever you have to shade orange. Now, I'm not quite finished with this graph because in this case with the discrete variation, what I need to do is not only stipple the line green, but I also have to stipple the integer points green as well. Now this is going to take some time. Ideally, you would have all of these stippled green, all of the points of intersection with the integers. That will take you some time. Again, if you look on page 299, you see that graph done beautifully for you. Mine, again, pretty good. I think so. So if you have any questions about example 2, please bring them to class tomorrow and we'll discuss them. Right now, we're going to move on to the your turn. It says boundary of a linear inequality is vertical or horizontal without a linear inequality. I'm going to press play on the button here. We'll watch the video, listen to the person with the lovely voice, and hear what they have to say.
I can tell that the boundary of a linear inequality is vertical or horizontal by simplifying the inequality. If the resulting inequality has only one variable, then the boundary is vertical or horizontal. I use the inequality x minus 2 is greater than 0 as an example. The boundary line is x equals 2. When the boundary line contains the variable x but not the variable y, it is vertical. I can verify this by graphing. The linear inequality x minus 2 is greater than 0 has a boundary line that is vertical because x must always have the constant value of 2, while y can take on any value. As a second example, I used the second inequality in example 2. I simplified the equation of the boundary line for this inequality. In the equation of the boundary line, x can have any value, but y has a constant value of 3. The boundary line is horizontal. I can verify that the boundary line is horizontal by graphing the inequality. If a linear inequality has only one variable, and this variable is x, the boundary of the inequality is vertical. If a linear inequality has only one variable, and this variable is y, the boundary of the inequality is horizontal.